Okay, so in this video, I'm gonna introduce spinor fields and the Dirac stuff in a very practical way. So basically, we've seen so far, we've quantized theories that contain scalar fields and complex scalar fields. And we saw that when we quantized the theory with, this real scalar field that just gave rise to excited states that looked like spin zero particles. And when we introduced complex scalar fields, we still got spin zero particles, but we also got antiparticles. And so there's kind of an indication that if we include different kinds of mathematical objects in our Lagrangian, we get more properties of our states. And one thing that was nice about these things is that they transform kind of nicely under Lorentz transformations. So it's easy to build a Lagrangian out of them because, for example, the scalar field transforms, pretty much automatically like like it should. So we can just have, powers of scalar fields and do whatever we want with them, basically. And we will be guaranteed that we'll have a Lorentz Invariant Lagrangian. And then similarly with the complex scalar fields, although we usually have, psi and psi dagger, it's always paired. And we've even seen vector fields, usually in the form of these derivatives, and those transform in a slightly more complicated way. But if we contract to Lorentz vectors, that will transform like a Lorentz scalar. So basically this, the one with the upper index transforms like this, the one with the lower index would transform the lambda inverse, and so those would cancel, and yeah. So it's also easy for those. And so we're going to introduce a new object called a spinor, and it's going to have 4 indices, just like a 4-vector, but it's not a 4-vector. And in practice, it's going to be useful to think of them, to work with them as row vectors and column vectors. And they transform in an even more complicated way than the Lorentz vectors. They transform according to this matrix S. And importantly, if you so since it transforms like this, if we take this product here, so again, this is like a row vector psi, the Hermitian conjugate of, so psi is like a column vector, so psi, the Hermitian conjugate of psi is like a row vector, complex conjugate. So this product is like a scalar, and it transforms like this. And basically, if S were unitary, then this Hermitian conjugate would be the same as the inverse, and this would cancel, and so it would be what we wanted. But as it turns out, S is not unitary. So you have to figure out, so what that means is there's not an obvious way yet to construct a Lorentz invariant Lagrangian using these objects. So we need to fix that. So these are just some definitions, basically, of these S matrices. Basically, they're matrices that satisfy, well, I guess they're defined as this commutation relation with these gamma matrices. And these gamma matrices are just any matrices that satisfy this anti-commutation relation. And then a couple of properties are that the gamma 0 squared is the identity, and gamma I squared is minus the identity. And we'll use those later. And so basically you can relate S dagger to the inverse of S with gamma 0 here. And knowing that, you can define a new, I guess, Dirac conjugate field as this. And this product of psi bar psi, if you look at how that transforms under a Lorentz transformation, you see that it transforms as a Lorentz vector, or as a Lorentz scalar, sorry. So what that means is we can have this product in our Lagrangian, and that will, is safe to have. That will ensure a Lorentz invariant theory. And then lastly, you can also have the gamma mu sandwiched between psi bar and psi, and that will transform as a Lorentz vector. So as long as we contract this thing with another Lorentz vector, we'll also get, that'll be something that transforms like a Lorentz scalar, so we can have that in our Lagrangian as well. And that's all we need for the thing that we're going to study, which is the Dirac Lagrangian. And as you can see, there's two terms here. One term involves gamma mu sandwiched between psi and psi bar and psi, and contracted with a d mu. So this term will, since we're contracting two Lorentz vectors, that will be safe. And then the other term just involves psi bar and psi, and that again is safe. So